And so section 1.1, some basic mathematical models. And first they're talking about, well, direction fields. That you have some differential equation is of the form dy over dx equal f of xy for some function f. So what you can do is the following. At some point, let's say this is the point x, y. So you pick some point x, y in the plane. You then say, well, at x, y, it's equal to -2, let's say. So then your derivative would equal -2. So we would say, oh, you have a tangent line in that has a value of -2. So you go over 1 down 2. Voila. That's your tangent line. So you would just draw your tangent line and you'd make it into a vector. Maybe, you know, this is your vector here. So you go over 1 down 2 or whatever I said it was. And so you do that for every point in the plane. So do that for every point in the plane. Then we call this picture a direction field. So somehow you can look at the plane and you can sort of see, well, and I'll tell you, to a differential equation by looking at this direction field, by looking at what are called integral curves. And so let's sort of do this. I might not erase this because this is just a picture. Yeah, I'm not going to erase this. I'll just sort of say it. Okay, so page number 7. In each of the problems, 1 through 6, draw direction field. For the direction field, determine the behavior of y as t goes infinity. If this behavior depends on the initial value of y at t equals 0, describe the dependency. So I have here y prime equals y plus 2. So let's say I'm at y equaling 1. So then this always has a slope. Direction. Is it the same as your slope field? I'm trying to think, is there any instance where a slope field is not the same as your direction field? See, because a direction field is always associated with a differential equation. Is a slope field always associated with a differential equation? Not always. The answer is yes, they are. They are the same term, and it is the same idea, but usually a slope field is not the used in the same context. And so, is it the same? Yes. Is it used by differing people to mean the same thing? Yes. But not all slope fields are generated from differential equations. Yeah. Right. So you're not going to, so when solving differential equations, just call it a direction field. It is, because the same thing that you do is the same thing you did for slope field. And so So just now say slope field. That's all I would say. Okay. Okay, so okay, good. Okay, so let's say we're here at 0. If I was here at 0, then the slope would always be 2, because y plus 2 is always going to equal 2. If I'm here at 1, y equal 1 along that line, then the slope is always going to be 3, because y plus 2 is always 3, etc. If I'm up here at, let's see, 1, 2, 3, 4, this will always have a slope of 6. If I'm here at y equal -1, always has a slope of 1. If I'm here at y equal -2, always has a slope of 0. So these are always going in this was 0. It's a horizontal line. If we're here at -3, it has a slope of -1, -4, -2, -5, -3, etc. So now let's draw some integral curves. So curve, I'll start somewhere, and I will then proceed along the direction as determined by this direction field. Did you always hear, they could have also said things about vector fields and other things. So there's some other terminology, but for differential equations, we really use the terminology that it's a direction field. Okay, so, and we call these things here integral curves. These individual curves here are really solutions to an initial value problem, where you start here and then continue on with this, well, direction. So, well, you notice that if initial value is greater than -2, you go off to plus infinity. If it is less than -2, you go off to negative infinity. So if it's what did I say? If it's less than -2, you go off to negative infinity. If it's greater than -2, you go off to positive infinity. And so, if you multiply this guy here by -1, then you're going off to plus infinity. So that's why I said it this way. And so if you are greater than -2, then it goes off to plus infinity. If you're less than -2, then this is negative times whatever this is, goes to plus infinity. So a -1 times y goes off to infinity. So it says that y goes to negative infinity if y sub 0 is less than -2. So this is your particular asymptotic behavior. Any questions about that? Here's a question. When they talked about slope fields, did they talk about integral curves? Probably not, because it probably wasn't given in the context of a differential equation. A hint of it. Oh, they gave a hint of it. Okay. Oh, okay. Okay. Okay, then let's go on. Oh. So, as I said, if you look in the other direction, if you go to go backwards in time, then it always goes to -2. So if you trail these backwards in time, notice that they're always approaching -2. And so y approaches -2 as t goes to negative infinity. Oh, we learned it. Oh, yeah, differential equations. Oh, is that why? Ah, okay. So they probably gave you this sort of picture uh, of differential equations in your calculus class, and they didn't really solve anything. They just sort of pictures like this. Okay, the qualitative analysis. Okay, so a spherical raindrop evaporates at a rate proportional to its surface area. Write a differential equation for the volume of a raindrop as a function of time. Oh, so maybe I should erase this. Okay, so I have a spherical raindrop. So I have here a raindrop, and it is spherical. Let's say that this is of radius r, and I know that the surface area of a sphere is 4 pi r squared. Now, do you really care if it's 4 pi? Not really, because you were always talking about proportionality in this problem. But if you know what the surface area is of a sphere, it's 4 pi r squared. And what's the volume of a sphere? Now the volume is 4/3 pi r cubed. Okay, so it says that the raindrop evaporates at a rate proportional to its surface area. So the rate of change of what? Was it, well, when you say something evaporates, well, how is it evaporating? Well, it changes with respect to time. So if I'm saying that something's evaporating, well, it's evaporating, meaning it's changing with respect to time. What's changing? Well, evaporation really means that its volume is getting less, right? If you have a gallon of water and half of it evaporates, well, then you have half the volume, right? So somehow your things are evaporating. And so I have that somehow, oh, and this is not alpha. This is proportional. And so I have that the derivative of the volume with respect to time is somehow proportional to its surface area. Now, I'll have that the constant proportionality, somehow this has got to be negative. Why is it negative? Because it's evaporating, meaning that its volume is getting smaller and smaller. So I want at the end that this has a negative proportionality. So this proportionality. Yes, the volume is changing with respect to time. Why? Because it's evaporating. If the volume didn't change, if the volume never changed with respect to time, it's not evaporating volume. It's, if you have 1 gallon of water and 10,000 years later you still have 1 gallon of water, well, it didn't evaporate. It just stayed 1 gallon. So if your 1 gallon of water evaporates to half of its size, so you only have half a gallon, well, then its volume has changed. Okay? And so if the volume has changed, well, then somehow we have that the volume is changing. It's evaporating, and it's evaporating, meaning that the rate of change here has to be negative because it's getting a smaller volume. You know, if you started out with 1 gallon and you have 2 gallons, well, I don't know. Somehow you're creating water. You know, so somehow it's not evaporating. It's you know you had a water faucet on or something. It's somehow not evaporating. It's getting bigger. Okay, so now let's see. Well, I want to do this as a rate. Okay, so I have here that dV dt, let's call it minus CS, where C is some constant. So let C be some constant proportionality, it's just some constant. And so I have here that that's equal. Now notice the following, that S, and maybe, is 4 pi r squared, right? And V is 4/3 pi r cubed. So that says that S is somehow related to r squared, and V is proportional to r cubed. So this says that R is proportional to, by the way, you could actually figure out the constant proportionality, but I'm not going to do it, is proportional to the square root of S. Therefore, V is proportional to S to the 3/2. Okay. And so that says that S is proportional to 2/3 of V. Okay. There's actually an easy way to figure out what the actual rate of proportionality is, but I'm not going to. So this says that, well, dV, actually I didn't need, maybe I'll do that at the end because I'm going to do it right now. I don't really need that because I'm going to do it at this second here. So now let's plug in. So I have S is proportional to V to 2/3. So from what I've written here, dV dt is proportional to minus S. So minus V to the 2/3. And so now I can give you a differential equation from this. So now I have that dV dt is equal to, let's say, minus K V to the 2/3, where K is some constant proportionality greater than 0. And that is my differential equation. By the way, this is how a lot of differential equations are sort of derived. So dv dt equals minus k v to the 2/3. So that is a differential equation, and that can be easily solved. And so I've changed this to something that we can actually look at. And if you look, well, it's very reasonable to think that evaporation is proportional to surface area, right? The more surface area you have, well, the more heat occurs. Where does heating occur? Heating occurs along the surface area. So your evaporation should be somehow proportional to your surface area. So this is a pretty is a fairly accurate sort of differential equation for figuring out, well, how does a spherical raindrop evaporate? And so a spherical raindrop should evaporate according to this that we just derived. So it's kind of strange. It's how in the world do you get v to the 2/3? Well, it's very logical